Good morning, everyone. Welcome to the final day of the 33rd edition of Soup and Science. Before we begin, we acknowledge that McGill University is on land which long served as a site of meeting and exchange amongst Indigenous peoples, including the Anishinaabe and the Haudenosaunee nations. We acknowledge and thank the diverse Indigenous people whose footsteps have marked this territory on which peoples of the world now gather. I'm going to turn the microphone over to Professor Bruce Lennox, who is the Dean of the Faculty of Science.
Thank you, Preeti. It's great to see you all, have you join us this morning. This is one of the most important event. It's a week-long event in the calendar in the Faculty of Science. It's a tradition that's now, as Preeti said, it's 33rd edition. So, this now includes the summer editions of this, and it's something that when I meet graduates from 10 years ago, they often make reference to Soup and Science as their first window into what research is, but also often the first window into who their professors are, because every professor at McGill in the Faculty of Science, at least, is both a teacher and instructor. They're in your classrooms, but they're also researchers, and so it's a lot of juggling of time and mindset, but it's great to have them join you today and telling you about what they're doing. We have four great speakers today. We have Professor Christie Rowe from the Department of Earth and Planetary Sciences, Professor Lena Simine from the Department of Chemistry, my home department, Christian van Sperber, Department of Geography, and Anna Weinberg from the Department of Psychology. So after their presentations, and many of you have probably been at the earlier Soup and Science, so you know that these are timed and that they're very precise timing in these. So it's a challenge. Believe me, it's a challenge for any professor to talk about their work in 3 or 4 minutes. When 3 or 4 hours is probably also a restrictive challenge. But we're going to hear what they're doing, and you're going to have a chance to interact with them. But following those presentations, you're going to have the opportunity to ask questions, and there'll be a skill testing question sort of game, and the top 10 students will be receiving prizes of gift cards at the LeJames bookstore, $25 gift cards. And there'll be a moderated Q&A session in the breakout rooms. And then, just before we're finished, we'll all return back to the main setting and just have a recap on what we've heard. So maybe I'll start then with our first presenter, Professor Christie Rowe from EPS. Christie, over to you.
Thank you. Sorry. Okay, so I'm going to talk to you about something that I've been working on only for the last couple of years. So my research, I'm a geologist. I look at rocks. And for the last couple of decades, I've been looking at rocks that either they're from faults that produced earthquakes, or rocks that were damaged by earthquakes, to try to understand the physics of earthquakes. And you might not think of Quebec as being a very seismically active area, but in fact, it is maybe the most active area in North America for earthquakes that's not on an actual tectonic plate boundary. And so where we live in Montreal is in the Western Quebec seismic zone, which I'll come back to in a minute. So if you've never experienced an earthquake, this little video will be useful to tell you what it might feel like. So these are GPS stations all over Japan. On the left, we have horizontal, and on the right, we have vertical, and the red arrows. And this is the waves propagating across Japan after the 2011 Tohoku earthquake. So I was fortunate enough to represent Canada on a research expedition on the Japanese ship Chikyu that went to the source of this earthquake, which is offshore the east coast of Japan, to drill into the submarine sediments and try to locate the actual fault. That is the break in the rocks that slipped up to the surface and produced this earthquake and tsunami. But most of the time I work on land. And I've been thinking especially lately about not just like the break in the rocks that produces the earthquake, but then all the motions before and after that lead up to it, that sort of like cue up the earthquake on the fault. So here's an earthquake that happened a couple of years ago in Northern California. On the day of the earthquake, the fault broke across several roads in the city of Napa, which you may know as the center of the wine industry in Northern California. And this, on the left, you can see the effect of the earthquake offsetting a stripe on the pavement by a few centimeters. But what they discovered because of quick response to the earthquake and going out there and checking it out was that another day later, the fault had continued to silently creep and even offset as much as the earthquake itself. So doubling the amount of slip on the fault. So earthquakes can be very damaging, but if the fault creeps really slow for a couple of days afterward, that's not damaging, but it's also kind of releasing some of the tectonic stress. I'm really interested in this process because studying this might tell us the difference between like when damaging earthquakes are likely to occur versus other kinds of motions in the faults that are less hazardous. So in California, which is where I'm from, it's known for earthquakes. It's known for active faults. And in 1857, there was a big earthquake in the East Bay, east of San Francisco, on the Hayward Fault. And then in 1923, the University of California built their football stadium right on the edge of a nice hill where it happened to be sitting on the earthquake generating fault. So here's the Berkeley football stadium seen in a digital elevation model that was made from lasers sent from a satellite from LiDAR. And here's the red line shows the fault where it cuts right through the stadium. And it only cuts through the stadium a little bit because the stadium's only been there since 1923. Let me just forward. Here's the stadium, the offset in the stadium since 1923. You can see that the wall is offset a little bit along that fault. Now, over here in Hamilton Gulch, there's like a creek that comes down the hill and goes across the fault. And there's a big old step in the creek. So the river flows down, takes a jog, whoop, over and down. So the creek is much older than the stadium. So in the time that the Hayward Fault has been moving with earthquakes and with creep in between, the gap of offset has gotten much greater. So the older a feature is, the more offset it is, the easier it is to find this fault. So if the geologists and engineers in 1923 had known about this phenomenon, they may not have built the stadium directly on top of the trace of the fault because the Hamilton Gulch offset shows us exactly where the fault should be found. So the younger the material is, the harder it is to find the faults. And this is a beautiful cross section, actually, of a fault that's cutting like into the page. It's a big active fault off the coast of California. It only touches the coastline in a few places where we can actually see it. And these sandstones down here are 8 million years old, and there's lots of little cuts and fractures here going up. And then there's what we call an unconformity, an age gap in the sediment here. And this gritty sand on top is only 12,000 years old. And it's very hard to find the fault slips in here. So luckily it's cut down so we can find it in the 8 billion years old sediments because then we can see a lot of offset there. So fast forward to Quebec. The climate is quite different here. And in fact, this diagram shows the ice sheet that was completely covering this area at the last glacial maximum, which was only about 22,000 years ago. So it was all covered with ice, scraped off all of the surface sediments and stuff, left a bunch of just boulders and clay and junk and lake sediments and sandy river sediments and just like geological junk all over the landscape, and finally receded off this area about maybe 12,000 years ago here in the latitude of Montreal. So that means everything we see on the surface is actually geologically very young. And if there's faults cutting through here, they are only going to have a little amount of time to make an offset or make a surface expression so that we can find them. But paradoxically, we have a ton of interesting earthquakes that have happened here in the last several hundred years since we've had recorded data. So some of these very ancient ones, like the 1732 one that occurred, as far as we can tell, in Montreal, like under the city, we have to reconstruct the past of those events from oral histories or written reports of the day. Insurance fraud has been really instructive way to get information about past earthquakes and all over the world. But so all of these earthquakes are quite big and would be severely damaging to today's infrastructure and population density if they occurred again. And this is only a couple hundred years of earthquake history. So this is actually like quite a large number of earthquakes. So you can see that they're centered, a lot of them are around the St. Lawrence Valley. There are some big ones that go up toward the Abitibi, like that's the Western Quebec seismic zone. And then there's a big patch here of lots of earthquakes around Charlevoix, because that area is actually an ancient impact structure that damaged the crust. So the crust of the earth is more prone to earthquakes there. And we don't totally understand why, but you can see that there's a big concentration of earthquakes there. So how are we going to find these earthquake faults in this crazy Quebec subglacial landscape of young sediments? Well, here's one that was just discovered by an undergraduate researcher in my group. I'm not going to tell you exactly where it is because we're in the process of verifying it, but it's only 75 kilometers from Montreal. So this fault or a fault like it could have been the one that produced that 1732 earthquake. And it's very subtle. This is the fault trace here. And you can see that there's some forested land, there's some farms. The farmers probably plowed across it a few times without even seeing it because it's just a small offset. And here is Aube in the last fall checking this out. So here's what it looks like when you're actually in the woods. You might not even notice it. It's just a little bump in the forest, but it has the potential to be a pretty historically important fault and potentially active for the future. So if I may put in a quick plug, if you're interested in learning more about the geology of Quebec and about field methods in geology, I give a course every fall. It's called EPSC 240, Geology in the Field. It's for people with zero background and zero expectations of knowledge in the earth sciences. So it's a great way to get introduced to geology. And we also look at climate, hydrology, lots of other field sciences that are active in and around Montreal. So please email me if you have any questions, and I would love to talk to you about this more or look at my class. Thank you very much for your time.
Oh, Bruce, you're on mute.
Thank you, Christie. Fascinating. I've been here in Montreal for about 35 years, and I've experienced at least half a dozen pretty significant earthquakes, including one that took out all of the stocked and canned food in the Metro store in Westmount. Everything was scattered, so it's pretty significant here. Very good. So let's move on to our next presenter, as Professor Lena Simine from Department of Chemistry. Over to you, Lena.
Thank you very much for the introduction. I'll share my screen. Let's try to do this again. Can you see my screen without anything else? Okay, looks good. All right, so I do have only 2.5 minutes to talk about all of the research that's happening in the lab. And I think I'll talk very, very quickly, very, very fast. So thanks very much for having me over for Soup and Science. Again, my name is Lena Simine. I'm an assistant professor here in the Department of Chemistry. And in my group, we do chemistry, but we do chemistry on a computer, which means we don't technically touch any chemicals with our hands, but we think very hard about them, and we try to find very interesting phenomena and very interesting new materials. So let me find my mouse. All right, so we are looking for interesting materials that may one day enable the design and engineering of exciting devices, for example, such as shown on the slide, organic photovoltaics, bioelectronics, biosensors, and other futuristic devices that exist already as prototypes today, but they have not been optimized for use and so you can't find them on Amazon. You can't buy any of those devices on Amazon. And so the common theme in all of these futuristic devices is that the materials that are used are very soft and very disordered, very amorphous. And so it's very, very hard to invent them, to design them, to find them, to synthesize them, because soft materials are very poorly understood. And so our goal is to use simulations to find materials that could make such devices happen. And in a way, we could summarize our work as hunting with a simulation for new materials. So because it's so hard to simulate disordered molecular structures, using traditional approaches to simulation is somewhat restrictive. And so we tried something new. We tried to use the algorithm that is currently used for art generation in the artificial intelligence community. One that is famously used for generation of those funky AI art that everybody makes fun of on the internet. And so the question is whether we could use that kind of algorithm to generate molecular structures at maybe cheaper and maybe reduced cost and maybe even improved accuracy. So the question is whether we can get away with it. Can we do this? And it turns out that we can. And here is an example of our simulation of a sample of aggregate of quantum dots that were generated through some kind of very fast drying process, and they just aggregated in this amorphous fashion. And we're able to simulate this obviously at linear cost. You can see that the printer head of the simulator just moves one pixel at a time and generates the picture. So if we want a sample that is, say, sample that is 25 times larger than this, all we need to do is to engage 25 times as many workers, so to speak, workers, 25 times more computers. And so instead of the exponential explosion in cost of going from a smaller simulation to a larger simulation in traditional molecular dynamics simulations, we get linear cost simulator this way. So this is a new development that was we developed last year. And now we're trying to apply it to interesting materials. For example, we we started from this newly synthesized material that is called the monolayer amorphous carbon. If you guys have heard about graphene in the past, this is a amorphous variant of graphene. It's like graphene that is all messed up. And so it's very new. It's very, very interesting. Nobody knows what to use it for, what it's good for, what it can do. And so we use our simulations to try to understand how it works, starting from nanoscale to all the way to mesoscale. And that's all I can tell you today because I have very little time. So I'll stop here, and I'm very happy to talk about this more in the breakout room. And thanks very much for our sponsors and to the audience for listening. Thank you very much.